All right, we need to learn Newton's laws, and we're going to start out with Newton's 3 laws of motion. Newton's 3 laws of motion. These are presented, Newton presents these in the Principia Mathematica Philosophiae Naturalis. The truth is that Newton really didn't invent these laws of motion. Most of these were worked out by Galileo and other people before Newton, but he codifies them, he organizes them, and then he uses them as the starting place for all his work, and then he proposes his law of gravity, which is wonderful and amazing, and then follows upon this. But first of all, we got to do Newton's laws of motion if we're going to understand how things move, both here on Earth and in space and throughout the whole universe. So, Newton's first law is the law of inertia. And the essential idea of the first law is to explain how will things move if there's no net force on it. If there's no force at all, or just if you add up the forces and they all sum to 0. So, if there is no net force on an object, what Newton says is it will move in one of two ways. Either, if it begins at rest, then it will remain at rest. It will either remain at rest, or if it has some initial motion, if it's already in motion, then it will continue to move at a constant speed in a straight line. Or it will move at a constant speed in a straight line. Now this is a big idea. This is a revolutionary idea that comes out of the scientific revolution, the Renaissance period, and all this, that forces are not necessary in order to make things move. If you go back to the ancient Greek ideas, Aristotle had asked, what makes things move? And Aristotle said, forces things move. In order for an object to move, there must be a force on it, pushing it. And Newton and Galileo and then the Renaissance people say, no, it is not necessary to have a force on an object to make things move. That motion is the way that motion is natural to object. Once you have an object going, the natural way for it to move, if there's no force on it, is for it to just keep moving at a constant speed in a straight line, and it would require a force to stop it moving. That forces would be required to prevent it from moving anymore. So once you get something going, it's just going to keep going and going and going forever at a constant speed in a straight line, unless some force acts on it to stop on it. Let's do a quick example of this. Suppose I am standing here, and suppose I am here, and I have a string, and on this, at the end of the string, I've got some mass, some rock, I don't know, Todd, then I'm whirling it round and round my head in a big circle. So here's my string, here's my mass, and this is going round and round me in a circle, and it's going round and round and round. And why is it going round? Well, there's the force of the string, which is holding it in its motion. But suppose it gets around to, I don't know, it gets around, it's going round and round, and then it gets to a certain point, and the string breaks. And the string breaks, so there's no more net force on it. So all of a sudden the string breaks, the force goes away. How will the rock move then? Well, it's going around and all this sort of thing. It gets to here, and you might kind of think that, okay, it's got some force on it, so you would tend to think that, usually people expect that, it's gonna then move off this way, because you can feel that tension in the string. But the answer comes from Newton's first law. If this object is in motion, and it is, and there's no net force on it, well, as soon as the string breaks, there's no net force on it, then what happens? Then it will continue to move at a constant speed in a straight line in the direction it was going at the point where there became no force on it. So at this point right here, which way was it going? Well, it's moving tangent to the circle, and so this object will not go off in this direction. Instead, it will just keep going tangent to the circle. It will go off in this direction. The string breaks, and that doesn't go flying off, it goes flying tangent in this direction. It's going the exact direction it was going at the instant the string broke, and now it's going to keep going at a constant speed in a straight line. Newton's first law. If there's no force on an object, then it will either remain at rest if it started at rest, or it will move at a constant speed in a straight line in whatever direction and velocity it happened to have at the instant that there became no net force on it. All right, cool. Newton's second law is even more important. Newton's second law says, okay, now if there is a force on an object, then how will it move? It can be written in simplest form as F equals ma. Force equals mass times acceleration, and this force is the net force on an object. So if I know what the net force on the object is, and I want to know, well, how will it move? Well, what this equation says is that forces cause things to accelerate. Forces cause acceleration. If I want to know the exact amount of the acceleration, well, I can reorganize the equation a little bit, and I can say, well, acceleration equals force net divided by mass. If I divide both sides by the mass, I get this. So if I know the force on an object and I know its mass, I can then calculate, well, how much is it going to accelerate? That's what forces do. You don't need a force to keep an object moving at a constant speed in a straight line, but we do need forces to change that. And then Newton also redefines what acceleration is. Now, in ordinary speech, when I say acceleration, I mean getting faster and faster, but Newton says no. The forces, the action of forces are more broad than that, so he redefines the word acceleration. So in astronomy and physics, we use acceleration in a much broader sense. And we say acceleration means some combination of three things. If you're accelerating, that means you can be speeding up. Speeding up, that's one form of acceleration. You can also be slowing down. Newton says forces cause that. If you're moving along and then you start slowing down, there must be some force slowing you down, so that's another form of acceleration. Slowing down, or what else? Changing direction. Changing direction. So from a Newtonian perspective, if you're speeding up, if you're slowing down, if you're changing direction, if you're doing anything other than being at rest or moving at a constant speed in a straight line, you are accelerating. Any object that is doing any of those things is accelerating. So that's an interesting thing. So if I look at an object and I say, ooh, that object's not moving at a constant speed in a straight line, it's changing direction, it's speeding up, it's slowing down, that means there must be a net force on that object. Net forces are what cause all of these sorts of things. So that's what forces do. Forces make things speed up, slow down, change direction. If I got this rock whizzing around me, even if the rock's going around me at a constant speed, well, it's changing direction. It's not moving at a constant speed in a straight line. Anything that's not moving at a constant speed in a straight line must be, or being at rest, must have a net force on it. And so it's the string which bends its path around into this. All right, let's take a look. That's Newton's first law, Newton's second law. Newton's third law of motion says, you may have heard, for every action there's an equal and opposite reaction. In modern language, rather than action, we'd say force. So I'll say this: for every force on one object, there is an equal and opposite force on another object. So, for instance, if I push on something, if I push on the wall, well, that would tend to make the wall move that way, and it would tell it to make me move this way. Now, the wall's attached down, and I'm standing on the floor. But if I was on roller skates, I push on the wall, and what happens? Well, I move backwards. If I push on one thing, the other thing pushes back on me. Or let's think about gravity. Right now, there's a force of gravity pulling me down to the earth. That's my weight. The force of gravity on me is my weight. And so gravity pulls me downward, and it's actually pulling the earth upward too. Now the effect on me is huge because, you know, if I jump, well, then the Earth's gravity causes me to accelerate downward. And remember, acceleration equals force divided by mass. My mass is relatively small, it's a big force, so I accelerate down toward the Earth a lot. Now when I jump or something like that, on the other hand, the Earth, that force of gravity from me pulling the Earth up, well, that force is the exact same as the force pulling on me, but the effect, the acceleration of the Earth is tiny because you take that force and you divide it by the Earth's mass. And the Earth's mass is huge. The Earth has this enormous mass, and so that force divided by its mass means that when I jump up, I do most of the falling. The Earth falls toward me, but a teeny tiny little bit. I'm almost completely indetectable because that force divided by that mass, divided by the Earth's mass, is tiny. But we both affect each other. Anytime you have any force anywhere in the universe, there must be an equal and opposite force on some other object. Forces exist in pairs. If I pull on this, well, then this pulls on me. And so these things exist back and forth all the time, no matter what. And those are Newton's 3 laws of motion, and they apply to everything in the whole entire universe.